Okay, so isoelectric point. In the last video, we went over amino acids. In this time, I'm going to go over the isoelectric point, which is the point at which a molecule carries no net charge and is electrically neutral. ISO is just basically a fancy word for equal, so that's a good way to remember it if you're a little bit confused. And Zwitterion, which will become a point important in a minute, as you'll see, is a molecule with an equal number of positively and negatively charged groups, but has no overall net charge. So, and then again, pKa. A pKa is the negative log of the acid dissociation constant. And what does that really mean? It basically just means that the lower the pKa, the stronger the acid. In other words, the more likely the molecule is to donate a proton. Remember, that is the the Bronsted-Lowry definition of an acid is a molecule that can donate a proton to solution. So if a solution is very acidic with a pH of 1, for example, this means that there are tons and tons of protons in the solution. So anything that can be protonated, so anything that can basically take on a proton will do so, to kind of almost think of it as to like neutralize the solution because there's tons and tons of protons. And vice versa, if a solution is very basic, there are very few protons in solution, so anything that can be deprotonated or can donate / lose a proton will do so and lose a proton. So I have here an amino acid. This is the basic general formula for amino acid: amine group, carboxylic acid, and a central carbon. So this, for example, is an amine group, has a pKa of about 9. This has a pKa of about 2. Somewhere in there. So if this can go ahead and accept a proton from solution, and this can donate a proton from solution. So this can exist as NH3, and this can exist as COO minus. And basically, one way to remember this, just as kind of another review, think of pH as like potential hydrogen. So if there's a very low pH, there's a very low potential hydrogen, like a very low for potential hydrogen, meaning there's tons and tons of protons already. So if there's tons of hydrogen molecules or protons, you don't need any more. So there's a low potential hydrogen. If there's not a lot of protons or hydrogens, then you could use a couple more. So there's a high potential for hydrogen. Okay, moving on. So this is just a reminder. So amino acids don't exist like this, which is their standard formula. They actually exist more like this, because at pH 7.4, which is the pH of the human body, they're going to go ahead, and this is kind of an important note. If the pH or potential hydrogen is higher than the pKa, that means that the subgroup is going to donate its proton, because the potential hydrogen is higher than its pKa, if that makes sense. Conversely, if the pH is lower than the molecule's pKa, then it's going to go ahead and accept a proton from solution. So the potential hydrogen is lower than the pKa, so it's going to go ahead and take a proton. So this is, so again, like I already reiterated this, recall or make sure you note that the pKa will be normally given to you, but it can vary. It's about 2. That's usually a good estimate. Sometimes it's more, sometimes it's less than 2. Same thing for the amine group. pKa is about 9, but it can be anywhere from 10 to 8.3. It varies. So just use the ones that are given to you. At general, at body temperature, or pH, which is 7.4, this is what amino acids are actually going to look like. The amine group is going to be protonated, and the carboxylic acid is going to be deprotonated. So then finding isoelectric point. The formula is actually pretty straightforward. It's just pKa1 plus pKa2 divided by 2. So right here again, pKa of the amine group we can estimate to be about 9, and pKa of the carboxylic acid we can estimate at about 2. Add those together, 11 divided by 2, 5.5. So the isoelectric point, the point at which this molecule is electronically neutral, is roughly 5.5. Kind of what does that mean? This is just like pretty much like the dead center sort of thing, if that makes sense, like dead center between the two pKa's. But in reality, like this is amino acid will exist as a Zwitterion anytime these two charges cancel out, which could be, pH 7, because at a pH 7 that's lower than this and higher than that. But this is the isoelectric point, which is, very important. Okay, so that's about it for finding an isoelectric point. But keep in mind, this is pretty straightforward. This is pretty straightforward for an amino acid like this. This could be, glycine, something like that, without a side chain that has a charge on it. But it gets a little bit more complicated if you have an amino acid that does actually have a charged side chain, because that is another variable that can either accept or donate a proton. So in the next video, I'm going to go over how you can find the isoelectric point of an amino acid that has a charged side chain. But thank you guys for watching. Feel free to stay connected. Please do, actually. And go ahead and watch video 3.